Hello, I'm Coleman Johnson from the University of Texas at Austin, and this presentation is about biopredictive dissolution testing and IV-IVCs for dexamethasone intravitreal implants in rabbits. This study was related to a commercial product called Ozurdex, which is a long-acting intravitreal implant comprising dexamethasone and a biodegradable polymer called PLGA. Ozurdex's patent protections have expired, but generic forms are not yet available. This is largely attributable to the cost and technical difficulties of demonstrating bioequivalence. In previous studies, we developed multiple formulations that were similar to Ozurdex. Two of these formulations, labeled EV and AK, displayed something quite interesting. So these formulations were similar in composition and physical characteristics and other things. They were different in that they used PLGA from different suppliers. The AK formulation, the Akina PLGA had a slightly higher residual monomer content. And with respect to performance, these two formulations showed a very similar release in a unbuffered saline dissolution medium, but release was quite different in a medium based on phosphate buffered saline. So that led us to the question, which of these in vitro methods is more biopredictive? In the current study, we performed a number of experiments relative to two study objectives. Our first objective was to assess the biopredictiveness of the two in vitro methods I just mentioned. So we did this assessment by comparing the in vitro drug release to the in vivo release of these two formulations in rabbit eyes. Our second objective was to investigate the physiological and physicochemical processes of in vivo release. First, we measured the buffering capacity of the rabbit vitreous using vitreous dissected from ex vivo eyes. In the interest of time, I won't discuss this data, but the rabbit vitreous, as well as the human vitreous, is definitely buffered. The other experiment was to measure the degradation of the PLGA matrix in the implant, both in vitro and in vivo. Starting with the in vitro drug release, this is the saline release curves of the two formulations, and this chart is the release curves in PBS. So the two major results are that the formulations look very similar in saline, but they're not similar in PBS, and the duration of drug release is a lot shorter in saline, about 28 days compared to 4 months. This is the in vitro drug release data. With regards to the methodology, what we did is we got Ozurdex injectors from an ophthalmologist clinic at the medical school here. We put our implants into those old injectors and then injected our formulations into the opposite eyes of 36 live rabbits. We recovered the globe and then recovered the remaining implant by dissecting. So here you can see the implant fragment in the rabbit vitreous. We measured the amount of drug remaining in the implant to determine how much drug had been released. We also measured the concentrations in the vitreous and aqueous compartments by LCMS. So there are three results here. So this is the in vivo release. First, the two formulations were not distinguishable. Second, the curves were similar in shape and also in duration to the saline data. And finally, both formulations were similar to literature data for Ozurdex from rabbit eyes. Here I want to discuss the in vivo concentrations measured by LCMS, as well as two forms of statistical analysis. In the first analysis, which is called pooled, this scatter plot shows the individual replicates, means, and standard deviations of the two formulations. And this chart shows the pooled data as a function of time. It's evident that the two formulations are similar, and we can say that there's no statistically significant difference, but that isn't proof that they are the same. The paired analysis, which is much better, this chart shows the individual replicates and lines connecting the two eyes of a given individual rabbit. Then here, This is the difference between the two formulations for a given rabbit, plotted as individual replicates, average and confidence interval. Then here we've plotted those differences as a function of time. The actual difference between these two formulations likely falls between somewhere within these 95% confidence intervals. These are also termed margins of equivalence. Another study would have to evaluate what margin of equivalence would be pharmacologically acceptable or how much variance occurs in the commercial product. Going back to the in vivo release curves, this left chart is an overlay of the in vivo and in vitro release in saline of our EV formulation. And then on the right, this is a IV-IVC chart showing in vivo release on this axis and in vitro saline release on this axis. So this shows the strong correlation of the saline method for the in vivo release. There's an interesting feature of this IV-IVC design. In a typical IV-IVC, you might manufacture and test multiple formulations with different in vitro release rates and expect to see a similar trend in vivo. This would allow you to build a zone of interpolation. However, in our study, we only measured one release rate, basically, and therefore we don't have a interpolation zone. However, this might be satisfactory in this context because we're only interested in one release rate, which is the release rate of the brand name product. Finally, we measured the time course of PLGA degradation in both in vitro methods and at critical time points in vivo to understand the in vivo release mechanism. This chart is the molecular weight of the PLGA matrix in the remaining implant fragment as a function of time. In all conditions, the PLGA matrix degrades by hydrolysis for the first 7 days. Water penetrates the implant by osmosis, and the osmotic gradient drives pure water into the implant without transfer of buffering agent. So all samples look the same over this first 7-day period. After 7 days, the matrix has degraded enough to form a network of interconnected pores and channels, which allows buffer to penetrate the implant. This percolating network is visible in these micro CT images we collected in a previous study. In saline, once that percolating network is formed, the implant continues to degrade both on the in the core as well as on the shell. And here, what we're measuring is just the remaining implant with a lot of those lower molecular weight degradants having been washed away. In PBS and in vivo, here we're measuring the molecular weight of the implant skin, which hasn't degraded significantly as it was exposed to buffer throughout the experiment. And the molecular weight goes up because the degraded PLGA in the implant core was washed away in that percolating network and is no longer contributing to this measurement. Despite the similarity in skin layer formation in PBS and in vivo, we still know that the implant degrades quickly in vivo. We know this because it becomes soft and disappears over 28 days, whereas the PBS samples maintain mechanical strength for months. So somehow there is an absence of buffering inside the implant in vivo. One possibility is that acidic PLGA oligomers cannot diffuse in the vitreous. They cannot escape the implant very well due to the presence of biological macromolecules that hinder diffusion. Another possibility is that the buffering species in the eye may be large molecular weight and also cannot diffuse into the implant. We've drawn the following conclusions. First, the PBS in vitro method is more biorelevant given that the rabbit vitreous is buffered. Second, saline is more biopredictive. The in vivo drug release was strongly related to rapid PLGA degradation, which occurred in saline and in vivo. Thus, neither saline or PBS are perfect mechanistic simulations of in vivo release. However, saline may provide a satisfactory IV-IVC relationship in the context of generic equivalence if the rabbit model is sufficiently representative of the human eye. This experiment would not be possible in human subjects, so it's an unanswered question if rabbit model is satisfactory for determining equivalence. Thank you.